Now let's consider how AI sees images as we continue with the mathematics of artificial intelligence. Now, here we'll be focusing on ideas like convolution and feature extraction. Okay, so applications and we have the applications of this in computer vision. Artificial intelligence can recognize faces, detect tumors, identify root signs, classify animals, and even understand satellite imagery. So unlike humans, however, AI does not actually see images. Unlike humans, however, AI does not actually see images. AI doesn't, just like AI doesn't understand English or our human language, but we are able to translate our human language into numbers for AI to understand and then piece it together and take it back to us. So AI cannot see images, right? Instead, it processes images as collections of numerical values and learns meaningful visual patterns through mathematical operations. So the invention of the convolutional neural network, CNN, revolutionized computer vision by allowing computers to automatically learn visual features directly from data. So in this lesson, you will learn how images are represented mathematically, why ordinary neural networks struggle with images, what convolution is, how feature extraction works, and you see pooling operations, building simple convolutional neural networks in Python, and applications of modern AI. So by the end of this lesson, you will understand how AI transforms millions of pixel values into meaningful object recognition. So our learning objectives, after completing this lesson, you'll be able to explain how computers represent digital images, distinguish between grayscale and RGB images, describe why traditional fully connected neural networks are inefficient for image processing, then explain the purpose of convolution rather in computer vision, then perform simple convolution calculations manually, understand the role of convolution kernels or filters, and explain feature maps and feature extraction. Then describe the effects of padding and stride, explain the purpose of pooling layers, understand how convolutional neural networks recognize complex objects, and build a basic convolutional neural network using TensorFlow slash Keras, then apply convolutional neural network concepts to real-world computer vision problems. So the skills you gain by the end of this lesson, you'll be able to represent images as matrices, apply convolution mathematically, compute feature maps manually, interpret convolutional kernels, build simple CNN architectures, and train image classification models, understand hierarchical feature learning, and explain why CNNs outperform traditional neural networks on image data. Now, the prerequisites, of course, before studying this lesson, you should be familiar with Python programming, NumPy arrays, matrix operations, basic neural networks, and forward propagation, as well as activation functions. This concept provides the mathematical foundation needed to understand convolution and feature extraction. So we go on to talk about why computer vision matters. Why does computer vision matters? So by the way, if you ask me, I like to see artificial intelligence. I like to categorize artificial intelligence into five. Depending on who you're talking to, somebody else can tell you seven or anything like that. But for me, I like to see that artificial intelligence has five parts. So one part of it, which I really love, is machine learning. So you have machine learning. Okay, I think I wrote artificial intelligence here. Should be artificial intelligence. Artificial intelligence. So you have machine learning. Apart from machine learning, you have natural language processing, natural language processing, NLP, natural language processing. So another branch of artificial intelligence is computer vision, which we are talking about in this video. You have computer vision. Then apart from computer vision, we have what we call expert systems. Expert systems like systems designed, like maybe I remember one of the earliest AI kind of thing we know is WebMD, where you go there and it's more you are talking to a computer like you are talking to an expert doctor, or you can have expert systems for law and different fields of specialization like that. And then of course for me another part of it would be robotics. Robotics. So for me, these are the the five branches of artificial intelligence. So somebody else may classify it differently, but these are the five parts I like. So for me, I'm really passionate about machine learning and natural language processing. I've explored machine learning a little bit. Natural language processing, I hope I'll get to it as at some point like that. So what we are doing today is about computer vision. And that's the question we're asking ourselves here is why computer vision matters. So, first of all, computer vision is the field of artificial intelligence that enables computers to interpret and understand visual information from the world. So every day, billions of images and videos are generated by smartphones, cameras, satellites, drones, medical scanners, and surveillance systems. Extracting useful information from this visual data manually is impossible at such a massive scale. So the goal of computer vision is to automate this process by teaching machines to recognize objects, detect patterns, measure distances, identify movements, and make intelligent decisions based on images. Unlike humans, who naturally recognize objects after years of experience, computers initially see only arrays of numbers. So computers don't understand language, they don't understand images, but they understand numbers. So AI must therefore learn how these numbers correspond to meaningful visual structures, such as edges, corners, textures, shapes, and eventually complete objects. So for real world applications of computer vision now, computer vision powers many technologies that people use every day. Like in healthcare, we have AI analyzing medical images to assist doctors in detecting diseases such as cancer, pneumonia, brain tumors, bone fractures, and diabetic retinopathy. And then we have autonomous vehicles. Self-driving cars continuously analyze camera images to identify roads, lane markings, traffic signs, pedestrians, cyclists, and other vehicles. So these detections allow the vehicle to navigate safely in real time. Then, of course, we have facial recognition. We have ideas in biometry and everything for identity verification and all that. So, modern smartphones unlock by recognizing facial features. Security systems also use facial recognition for identity verification. Examples include phone unlocking, airport security, employee attendance systems, and smart surveillance. So, in agriculture, we have computer vision helping farmers by detecting plant diseases, pest infestations, crop maturity, weed locations, and this enables precision agriculture and reduces waste. In fact, some countries are very advanced with precision agriculture to the point that they know what exact the amount of water every plant standing needs. They know that based on the location of this particular plant, this is the amount of water it needs. That's precision agriculture. And in manufacturing, we have computer vision. Factories use AI-powered cameras to inspect products for defects such as cracks, missing components, surface scratches, and incorrect assembly. Automated inspection improves product quality while reducing costs. And then we have retail. You have computer vision in retail. So stores use computer vision for automatic checkout, inventory monitoring, customer behavior analysis, and even shelf management like that. So if you get into a big mall and you think nobody's watching you, somebody is definitely watching. So you have satellite imaging. I mean, an AI is watching you, and that can help humans to watch you, right? Satellite imaging and computer vision analyzes satellite photographs to monitor forest cover, urban expansion, floods, wildfires, agricultural productivity, and climate change. Then we have the central question. A human immediately recognizes a cat, a car, or a tree without consciously analyzing every pixel. I mean, once you see it, you just know this is a cat, this is a dog, and all that. So, how does an AI system accomplish the same task? Now, that's where the issue is. The answer lies in two fundamental ideas: convolution and feature extraction. Convolution detects important local patterns in an image, while feature extraction gradually combines simple patterns into increasingly complex representations until entire objects can be recognized. More like you are picking parts and parts of an image and you aggregate it together, and then you can have an idea what the image looks like rather. This concept formed the foundation of modern convolutional neural networks, which dominates today's computer vision systems. So you have convolution and feature extraction. So convolution detecting important local patterns. So it's more like convolution is detecting these fine details, and feature extraction puts all these fine details together to form the whole picture. And then the computer can now say, oh, I think that is a cat, or I think that's a dog. Though it doesn't know dog or cat in real life, but it can see the pixels and everything. Now, how computer represents images now? Of course, like we know, just like in the case of words, computers don't know words, they know numbers. So Humans perceive images as meaningful scenes containing people, animals, buildings, and objects. Computers, however, do not possess visual perception. So, to a computer, an image is simply a rectangular grid of numbers called pixels. So, each pixel stores information about the brightness or color at a particular location. Machine learning algorithms analyze these numerical values to discover meaningful patterns. Now, the question is, what is a pixel? A pixel or a picture element is the smallest unit of a digital image. An image is formed by arranging thousands or millions of pixels into rows and columns. So for an image with height h and with w, the image can be represented as image. That's an h by w real number system for grayscale images, or image belonging to the H by W by 3 real number system for color images like that. So for grayscales, right, a grayscale image contains only one intensity value for each pixel. So typically, so you have big I of small I, comma j, line between 0 and 255. You remember the other in the last video we were dividing by 255. This is where that idea comes from. So where 0 represents black, 255 represents white. So black and white, that's grayscale, and values between them represent different shades of gray. So at say 2, you have more, it's more black than white. At 250, it's more white than black. That's exactly the idea. So values between them represent different grays of scale, different shades of gray rather. So for example, you have all these 15, so all these numbers 15, 20, 230, 200, all these values lie between 0 and 255. So it means 15 is blacker than 20. 230 is whiter than 220, like that. So each entry represents the brightness of one pixel, like that. So talking about color images now, color images consist of three separate channels. You have the red, the green, and the blue. These are the primary. No, these are really not the primary colors, right? Red, green, blue. I think yellow is one of the primary colors, right? I think so. So each channel, yeah, because I remember green is a combination of red and yellow. But in this case, it's RGB, red, green, and blue. So each channel is itself a grayscale. So thus, a color image is represented as HW. So you have the grayscale component and then the third one. So where the last dimension stores the RGB values. For example, a single pixel might have the value 25500. So it is 25500 like that. Then which represents pure red. So this represents pure red, while 02550 represents pure green, like that. And then and 00255 represents pure blue. So 25500 pure red, 02550 pure green, 00255. So it's more like it's not one, it's some kind of encoding which is not one hot. If you like, you can say maybe I don't know if it's okay to call it 255 hot encoding, kind of. So 255 corresponds perfectly with each of the RGB colors, like that. So we have image dimensions now. Suppose an image has dimensions 512 by 512. The total number of pixels will then be 512 by multiplied by 512, which is 262,144. So if the image is in RGB format, the total number of numerical values become 512 by 512 times 3, which is 786,432. So even a relatively small image therefore contains hundreds of thousands of numerical values. So just one image. So that's why it's a lot of computation going on when you work with images in AI. My goal here is to remove. I want to remove that. I saw something. Okay, there's a worked example there. Okay, I think let me just leave it alone. I can deal with that later. Yeah, so we have a worked example here. First worked ex is it the first one? Okay, I've gone too far. Yeah, so we have a worked example here. Imagine a smartphone captures an image with dimensions 1920 by 1080. So number of pixels will be 1920 by 1080. That's 2,073,600 pixels. The number of RGB values will have to be, so the number of pixels multiplied by 3, that's 6,222,800. Therefore, before any AI model begins processing it receives more than 6 million numerical values from a single color image. 6 million numerical values. That's a big one. And that's why compute power is such an issue with AI, right? So why this matters? Every object recognition system begins with these raw pixel values, and the challenge is that neighboring pixels alone do not explicitly indicate where objects begin or end. So a computer must therefore learn how combinations of pixels form edges, corners, textures, curves, shapes, and eventually complete objects. The mathematical operations that accomplish this are the focus of the next sections on convolution and feature extraction. So so it's a lot of mathematics behind this whole thing. Now, why traditional neural networks struggle with images now? Before the development of convolutional neural networks, researchers attempted to use ordinary fully connected neural networks for image recognition. Although these networks work well for many tabular data sets, they perform poorly on images because images are extremely large and possess strong spatial structure. So understanding these limitations helps explain why convolution became one of the greatest breakthroughs in artificial intelligence. So fully connected neural networks now. In a fully connected or dense neural network, every neuron in one layer is connected to every neuron in the next layer, right? So if the input contains n values and the hidden layer contains m neurons, then the number of weights is n by m. So remember, if you look the last video on building a neural network from scratch, you discover that when we want to compute the number of layers, the number of neurons or whatever, so we usually would multiply the the two numbers together to get the weights, and then the value of m is then the bias. So as the input increases, the number of parameters grow. As the input increases, the number of parameters grows extremely rapidly. So imagine this example one. Suppose we have a grayscale image of 64 by 64. The input layer therefore contains 64 by 64, which is 4096 neurons. If the first hidden layer has 1000, then 1000 neurons, then the number of trainable weights will now be 4096 multiplied by 1000. That's 4,096,000. So more than 4 million parameters must be learned for just one hidden layer. That's a whole lot. And that's why compute power is such an issue with AI, right? So what example two now? Now consider a larger image of size 256 by 256. The number of input neurons becomes 256 by 256, which is 65,536. Connecting this to a hidden layer containing 1000 neuron requires 65,536 times 1000, which is 65,536,000 weights. This is over 65 million parameters before adding additional layers. So, and you can have tons of layers like that with all these big values. So the problem of memory now. So every parameter occupies computer memory. So as image resolution increases, memory usage increases, training time increases, also computational cost increases. So large dense networks therefore become expensive to train. And then we can have lots of spatial information. Images contain important spatial relationships. For example, you can see you have two eyes, you have a nose, you have a mouth. But of course, we can see these are key features of a face, but there are other things. I mean, you have the skin, right? You have the ears and all of this. So the position of the eyes, nose, and mouth determine whether the image represents a human face. All right. So if you have the mouth at the top and you have the nose somewhere, so it can be like the face of a monster. So a fully connected network treats every pixel independently after flattening the image into a one-dimensional vector. Instead of preserving h by w, the image then becomes hw simply. So the neighboring relationships between pixels are largely lost in that case. So we have that kind of problem with loss of spatial information. So we have memory, and then spatial information can be lost because you just have plain numbers now. Consider the image 111,000,111. Flattening it produces 111,000,111 straight like that. The original two-dimensional arrangement is no longer explicit. Like here, I mean, we had some structure to this, but everything is just straight here. So as a result, the network must learn spatial patterns from scratch, making learning far less efficient in that case. And then we can have the trouble with overfitting. So these are some challenges we have with computer vision. So dense neural networks often contain millions of parameters. So if the training data set is relatively small, the model may memorize the training images instead of learning general visual patterns. So this phenomenon is known as overfitting. Okay, because the data set is so small that the model just learns everything as if just knows everything. But an overfitted model performs well on the training data, but poorly on unseen images. So if you bring the images, there's a problem there. Then you have lack of translation invariance. So here, basically, we are talking about challenges with neural networks, the big numbers involved, which is problem of memory. So we are talking about why traditional neural networks struggle with images. So we've seen fully connected neural networks. Every layer is connected. Then, yeah, and as a result of that, we have problem of memory, and we can have loss of spatial information. And then we also see the problem of overfitting. Then another problem is lack of translational invariance. Now, suppose a cat appears in the center of an image. A dense neural network may correctly recognize it. If the same cat moves to the upper left corner, the pixel positions change completely. So the network may incorrectly classify the image because it has not learned that the object is the same despite its new location. So humans naturally recognize objects regardless of where they appear in an image, but traditional dense networks struggle with this task. That's another problem. Now, convolution is the solution, right? Why convolution solves these problems? Convolutional neural networks overcome these limitations by examining only small local regions at a time, sharing the same filter across the entire image, then dramatically reducing the number of parameters, preserving spatial relationships, and automatically learning useful visual features. So convolutional neural networks now help us to solve all these problems in one blow, right? By preserving spatial relationships, automatically learning useful visual features, and all of this. So instead of connecting every pixel to every neuron, CNN learns small filters that detect edges, textures, corners, and shapes throughout the image. So this efficient strategy enables modern AI systems to recognize objects accurately, even in large, high-resolution images. Now, the question, introducing convolution, the core idea behind convolutional neural networks now. Convolution is the fundamental mathematical operation that gives convolutional neural networks their name. So we come across the idea of convolution under things like, is it under calculus now? Things like you have all these transforms, Laplace transforms, Z transform, and all of them. So it is the mechanism that allows AI to discover useful visual patterns such as edges, corners, textures, and shapes without being explicitly programmed to do so. Instead of examining an entire image at once, convolution analyzes small neighborhoods of pixels and gradually builds a richer understanding of the image. Now, the central idea is this. Imagine reading a large book like Terraja for electrical engineering, right? Rather than trying to understand every page simultaneously, you read a few words at a time and gradually build an understanding of the entire story. Then convolution works in a similar way. Instead of processing the whole image at once, a small window called a kernel, or what you call a filter, moves across the image one region at a time. So at every position, the filter measures how strongly a particular visual pattern is present. Now we talk about the kernel now. What is the kernel? A kernel is a small matrix of learnable numbers. So common kernel examples can include 3 by 3, 5 by 5, 7 by 7. The kernel is much smaller than the image. For example, if the image is 64 by 64, a kernel can just be 3 by 3. The same kernel is applied repeatedly across every part of the image. So it's more like you're moving gradually. It's more like you're sliding a window, over something like that. So, and when you have the mathematical definition, suppose that the image is I and the kernel is K, the convolution operation is written as F equals I star K, where star denotes the convolution. So I convoluted with K. So the image convoluted with the kernel. So F is then the resulting feature map we have there. So at each location, corresponding entries of the image and kernel are multiplied together and then summed to produce a single output value. Then we have step-by-step convolution process. For every kernel position, right, place the kernel over a small region of the image, multiply corresponding elements, add all the products, store the result in the output feature map, slide the kernel to the next position. So it's more like you're sliding, repeat until the entire image has been processed. So this process converts the original image into a new representation that emphasizes specific visual features. Now, the question is, why use small filters? Small filters are computationally efficient while still capturing meaningful local patterns. For example, a 3 by 3 kernel can detect vertical edges, horizontal edges, diagonal edges, corners, simple textures. So as multiple convolutional layers are stacked together, these simple patterns combine into increasingly complex structures. Let me see if I can get a picture of what we are talking about here. Filters or kernels. Filters or kernels. Okay. I think this image, okay, let me look at some images here. So this is the kind of thing you have all these projections onto things. So you have small windows. You have a 28 by 28 matrix and you have a 3 by 3 matrix just moving over it step by step like that. So that's the kind of thing happening. So well, then we have parameter sharing. So one of the greatest advantages of convolution is parameter sharing. Instead of learning a different set of weights for every image location, the same kernel is reused across the entire image. For example, consider a 3 by 3 kernel. So the total number of learnable parameters is 3 by 3, which is 9. Whether the image is 32 by 32 or 1024 by 1024, the kernel still contains only 9 weights, ignoring an optional bias term. So this dramatically reduces the number of trainable parameters compared to fully connected neural network, which we talked about before, that leads to very big values and memory issues and everything. So for local connectivity now, unlike dense neural networks, each neuron in convolutional layer connects only to a small local region of the image. So this property is called local connectivity. So because nearby pixels are usually related, local connectivity preserves important spatial information while reducing computation. So if you want to imagine a neural network as something like this, so say a you have a matrix like this. Okay, this is a 3 by 4 matrix, right? 3 rows and 4 columns. That's a 3 by 4 matrix. Now, imagine you now have a 2 by 2 kernel. So the 2 by 2 kernel is more like it takes a snapshot here. Then it moves to it then moves to say this so 2 by 2 here. It also takes the images in like this, and then next you have another 2 by 2. So it just keeps moving like that. Then it can even come down this way. Yeah, it can even come down this way, and then maybe you then have another 2 by 2 here. While at it, it's taking snapshots here and there, and then maybe finally you have so it just goes move around, or it can even come to the center like this, taking 2 by 2. So it now stacks all of this information, it gathers together to get the overall thing. So because nearby pixels are related, right? Local connectivity preserves important spatial information while reducing computation. So the intuition here is that suppose you are trying to recognize a face, you do not need to compare every pixel in the image with every other pixel. Instead, you first detect simple structures such as edges, curves, eye outlines, nose contours, mouth boundaries. These local features are later combined into a complete face. Convolution mimics this hierarchical learning process. So you pick pieces together through convolution, and then through feature extraction, you put everything together. You pick everything out by convolution, and with feature extraction, you put everything together. So advantages of convolution now. Compared with fully connected networks, convolution offers several important advantages. So you have fewer trainable parameters, lower memory usage, faster computation, better preservation of spatial relationships, automatic learning of useful visual features, improved generalization to new images, and greater robustness to object location within an image. So looking ahead now, you see that the convolution operation itself depends entirely on the kernel. So different kernels detect different visual patterns. And so next we will study convolution kernels in detail and learn how specific filters. So here, let's go ahead to convolution kernels or filters. So a kernel or filter is a small matrix of learnable weights that slides across the image during convolution. So like I showed the other time, you have this 3 by 4 matrix, and then you now have a 2 by 2 matrix that is moving, it moves here, takes gets the features there, then probably moves to the next one, gets the features here, moves here, get the features, and then maybe so it can also move like this, get the features, moves here, get the features, moves here, get the features, and stacks everything together. You then finally get the full picture. So, different kernels detect different visual patterns. Examples include vertical edges, horizontal edges, diagonal edges, corners, and textures. For example one now, imagine the vertical edge detector. You have 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. This filter responds strongly to vertical intensity changes. So example 2, you have horizontal edge detector. So this is vertical, right? 1, 1, 1, minus 1, minus 1, minus 1 for vertical. For horizontal, now you have 1, 1, 1 at the top, minus 1, minus 1, minus 1 at the bottom, and 0, 0, 0 in between. So this detects horizontal boundaries. And then you have the blur filter. So this smooths an image by averaging neighboring pixels. So K is 1 over 9 of 1, 1, 1, 1, 1, 1, 1, 1, like that. So modern convolutional neural networks do not use manually designed filters. Instead, they automatically learn the best kernels during training for sure. So, example, you want to perform a convolution manually. Consider the image I 301274156 and the kernel K 101010101. So if you multiply corresponding entries now, so you have 1 times 3, you have 3, 0 times 0, you have 0, 1 times 1, you have 1, 2 times 0, you have this, 7 times 1, you have this, 4 times 0, you have this, then 1 times 1, you have this, 5 times 0, you have this, 6 times 1, you have this. Put everything together, you get 18. So it then say that, so the convolution just multiplies corresponding values like that. So the output value is then 18. So this single value becomes one entry in the output feature map like that. Then you then have feature maps now. After applying convolution across the entire image, the outputs form a feature map. Suppose the input is 32 by 32 and the kernel is 3 by 3. So you have a stride to be 1, padding to be 0. The output size then is 32 minus 3, 32 minus 3 all over 1 plus 1. So that's 29 over 1 plus 1. That's 30. Therefore, you then get it. You have 30 by 30. So each number represents how strongly the filter detected its target feature at that location. And then we talk about the idea of padding. Without padding, images become smaller after each convolution. So to preserve image size, we add zeros around the border. So if input size is n, kernel size is f, padding is p, and stride is s, then output size is then input size minus kernel size plus 2 times padding all over the stride plus 1. So example, if you have input 5 by 5, padding 1, kernel 3 by 3, output 5 by 5. Padding allows convolutional neural networks to preserve border information like that. So that's where padding comes from. So adding zeros. So 28.8. So we started with 5 by 5 now. So after you get the kernel 3 by 3, you have zeros all around that to preserve the border information. Then you have the stride. Stride determines how far the kernel moves after each convolution. So stride 1 moves 1 pixel, stride 2 moves 2 pixels. Larger stride reduce computational cost, but also discard more information. So if you want to get more information, you want to move slowly, you don't want to move too many pixels at the same time. So you want to move fast enough to preserve, not to waste too much compute power, but you want to move slow enough to get all the information you should get. If you have an input of 8 by 8 and the kernel is 3 by 3 and the stride is 2, the output then will be 8 minus 3 over 2 plus 1, which is 8 minus 3, 5 over 2. That's 2.8 minus 3, 5 over 2. That's 2.5 plus 1. That's 3.5. So we take 3. So hence you have 3 by 3 in that case. Then for feature extraction now, the purpose of convolution is feature extraction. So early convolutional neural network layers detect edges, lines, and gradients. Middle layers detect corners, textures, circles, and curves. And deep layers detect eyes, wheels, doors, leaves. And final layers recognize faces, cars, cats, and buildings. CNNs therefore learn increasingly abstract representations as depth increases like that. So we also have hierarchical learning there. So feature learning occurs in stages. You have pixels, you have edges, you have corners, you have textures, you have object parts, you have complete objects. This hierarchy enables convolutional neural networks to recognize highly complex visual scenes using simple mathematical operations. Then we have pooling layers now. So pooling reduces the spatial dimensions of feature maps. So the most common operation is max pooling. So example, you have 3752. The pooled value will be 7, right? So you have the biggest value, which is 7. So advantages of that include you can easily just since you're only picking the biggest value, so you get faster computation, you have reduced memory usage, less overfitting and translation robustness. So instead of using everything, you just take the biggest value right there. So then so this is a manual convolution here. So import number as NP. So you have image array 1, 2, 3, 4, 5, 6, 7, 8, 9. Then the kernel is 1, 0, 0, minus 1. And you have the outputs, of zeros now. So for I in range 2, then for j in range 2, then you get the region for the image. So I plus 2, and you print the output. You have minus 4 all around. So this demonstrates how convolution is computed using NumPy without deep learning libraries. So it's more like doing that from manually from scratch. So you then have all this TensorFlow, Keras model, import sequential, convo 2D, max pooling 2D, blah, blah, blah. And then you have the whole code model. You have a sequential model. You have the input layer explicitly. So you have model.add. So let me start running this in case it's going to take a lot of time. So add the input layer explicitly. So you have model.add 28 by 28 by 1. Model add conv 2D 32 3 by 3 and all that. So you can then have a summary of the results. So here you have this a sequential model. So for the layer type convolution 2D, the output shape is none, 262632. Parameters, you have 320. Max pooling 2D, you have 131332. You have 0 for parameter number. Then you flatten, you have 54080 there. Dense, 128, that's 69352. Dense 1, you have none, 10, 1290. So total parameters now you have 693,962. I think that's adding up all of these things. Then you have trainable parameters 693,962, also taking 2.65 MB, and non-trainable parameters. So there are no non-trainable parameters, just 0 by. So this simple convolutional neural network can classify handwritten digits from the MNIST data set. Now we have the convolutional neural network architecture. You have this that a typical convolutional neural network follows this sequence. You have the image, then from the image there's convolution done, and then you have the rectified linear unit activation, then you have pooling, you have convolution, you have pooling again, you flatten, then you have a dense layer, you have a softmax, and you have the prediction. So each layer extracts progressively richer visual information. So applications of CNNs, I mean, we've seen some of them already. Convolutional neural networks are widely used in modern AI. Examples include facial recognition, medical image diagnosis, self-driving vehicles, OCR, fingerprint verification, industrial inspection, crop disease detection, wildlife monitoring, surveillance, security surveillance, satellite image analysis. Now, CNNs have become the foundation of computer vision, basically. And some common mistakes you can have in CNNs when learning convolutional neural networks, students often confuse convolution with ordinary matrix multiplication. So it is not ordinary matrix multiplication, it is corresponding numbers multiplication, as we saw the other time. That's what convolution is here. So they also forget to normalize image pixel values. So in the last video, we saw there's a point where we're normalizing normal pixel value by 255, which represents the grayscale number we saw it for white. They also ignore the effect of padding, choosing appropriate stride values, use too many filters for small data sets, overfit by building unnecessarily deep networks, forget that kernels are learned automatically during training. Avoiding these mistakes leads to more effective convolutional neural network models. So in summary, we have that uh I mean in this lesson we learned how AI interprets images using convolution and feature extraction. So key ideas include the following: that images are numerical matrices, then CNNs process local regions rather than entire images. Convolution applies learnable filters across images. Different kernels detect different visual patterns. Feature maps highlight important structures. Pooling reduces computation while preserving key information. Hierarchical feature extraction allows CNNs, that's convolutional neural networks, to recognize increasingly complex objects. CNNs power modern computer vision applications such as autonomous driving, medical diagnosis, facial recognition, robotics, and satellite imaging. Understanding convolution and feature extraction provides the foundation for advanced topics such as object detection, semantic segmentation, transfer learning, attention mechanisms, and vision transformers. So we have our practice problems as usual, and let's see, I may be able to do two of them if the time is good. Right. So yeah, let's see. Right. So we have you can see problems 1 to 10 here. For instance, I'll be taking care of problems 5 and 17. So 5, a CNN layer uses 64 filters of size 3 by 3 on an RGB image. How many learnable weights are contained in the convolutional kernels? So we are going to deal with that. And then so you can see question problems 1 to 10 right here. So next you can see 11. You should be able to see 11 to 20. So I'll be dealing with problem 17 again. A convolutional layer has 128 filters, each of size 5 by 5, operating on feature maps with depth 64. Calculate the total number of learnable kernel weights and ignore the biases. So if you add biases, you're going to have more computations to do. So let's go ahead and deal with problems 5 and 17. Problems 5 and 17. Okay, so problem 5. A convolutional neural network layer uses 64 filters of size 3 by 3 on RGB image, how many? How many? How many learnable weights? How many learnable weights are are contained in the convolution kernels? In the convolution kernels, if you ignore bias terms. Yes, so for the solution, right? Since the image is RGB, so each filter spans all three color channels. Therefore, the dimension of one filter, the dimensions of one filter are 3 by 3 by 3. So that tells us that the number of weights, the number of weights of one filter will have to be 3 times 3 times 3, which is 27, like that. So we have that. So the number of weights in one filter is 3 times 3 times 3, which is 27. So with that in place, we then say that since, so the question says there are 64 filters, 64 filters of size 3 by 3 by 3. And since we are dealing with RGB, we have 27 as the number of weights. So since there are 64 filters, the total number of learnable weights, is 64. So 64 filters multiplied by 27 weights, and that is equal to 1,728. So that tells us that therefore the convolutional layer contains 1,728 learnable weights, excluding bias terms. Excluding bias terms. We have that. Then problem 16, I think. Or is it 17? Problem 17. Problem 17. So it says that a convolutional convo a convolutional layer has 128 filters, each of size 5 by 5 each of size 5 by 5, operating on feature maps, with, so now we have a depth attached to it with depth 64. So calculate the total number, calculate the total number of learnable kernel weights, ignoring biases. So ignore biases. So here, if I pick this, we have the solution. So here, each filter must span the full depth. Each filter must span the full depth of the input feature maps. Therefore, one filter has dimensions. One filter has dimensions 5 by 5 by 64. So that gives us the number of weights too. So the number of weights in one filter is 5 by 5 by 64, which is 25 by 64, and that is 1,600. That's 1,600 like that. Then since there are 128 filters, the total number of learnable weights is 128 times 1,600. That is equal to 204,800, like this. So what's the interpretation of all this? Interpretation. Although the input feature maps, although the input feature maps may be very large, spatially, the number of learnable parameters depends only on one, the kernel width. And I want to change this now. One, the kernel height. Then next, we have the kernel width. Then we have the input depth, or number of channels. Then we have the number of filters and the number of filters. Okay, so this parameter sharing, this parameter sharing is one of the major reasons. It's one of the major reasons. So you have sharing of parameters there is one of the major reasons convolutional neural networks are far more efficient than fully connected neural networks for image processing. For image processing. So final answer, of course. So overall, the convolutional, the convolutional layer contains 204,800 learnable kernel widths, excluding bias terms, excluding bias terms. And that's how that goes. So, again, I'll just show you the problems. Try your hands on them. So you can see 1 to 10 all together here. 1 to 10 there. I've done 5 and 17. So 1 to 10, then 11 to 20, where I took care of 17. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to the channel already, I thank you very much for doing that. But if you haven't subscribed, this is a very good time to go ahead and subscribe. As you also subscribe, you can hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges you find when you click on join. Um, Ultimately, don't forget to comment, like, and share so that you can always so that other people rather can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.